When a new application hits the market, adoption usually ripples through a population in a predictable wave. But when you introduce a technology that routes personal, sensitive data into a centralized, government-controlled hub, that wave comes to a dead stop. For decades, researchers have relied on a standard model of technology diffusion, specifically Everett Rogers' classical framework, which categorizes populations into a smooth curve from early innovators down to late adopting laggards. That framework operates on a single underlying assumption. An individual's decision to use a new tool is driven primarily by their baseline affinity for technology. But that assumption falls apart when dealing with municipal infrastructure or public health apps that centralize data under a political authority. We see citizens happily surrender their digital footprints to commercial data mining operations every day. Yet those same populations frequently reject municipal smart city grids and government contact tracing programs. The existence of this privacy paradox suggests that standard diffusion models may be missing a critical variable when predicting how civic technology actually spreads. To accurately model this behavior, researchers are moving away from the single-axis diffusion curve. Instead, populations are mapped onto a two-dimensional plane. On this matrix, an agent's decision is governed by two distinct factors: their affinity for technology and their level of political trust in the managing authority. These two variables are modeled as orthogonal, independently distributed factors. A person's voting history and their enthusiasm for the latest smartphone hardware do not dictate one another. To observe how these independent variables interact at scale, researchers construct multi-agent computer simulations. By accounting for these overlapping networks, researchers can observe how individual decisions ripple through a community, creating a dynamic that is far more volatile than a traditional adoption curve. Building this agent-based model starts by defining the starting point, placing a single simulated citizen onto a two-dimensional matrix. This chart shows the baseline matrix. The y-axis tracks technological affinity: advocates, apathetic, and concerned. The x-axis tracks support for the government: trustful, neutral, or distrustful. Because axes are independent, extreme combinations exist, like a citizen who distrusts the government but is a high-tech advocate. The simulation generates a population where every individual is assigned a specific coordinate within this space based on starting ratios. An agent's propensity to adopt technology is strictly defined by this unique intersection of tech affinity and political trust. Tech enthusiasm alone is not enough. With the agents defined, we have to look at the environmental structure, specifically how information flows between these individuals. This diagram shows the first channel, word of mouth, representing digital connections. It is highly fluid, transmitting tech features. The second channel, word of mouth, represents deep familial ties. Unlike the digital layer, this rigid channel rarely changes, solely transmitting political trust. Because sensitive personal choices rely heavily on these close-knit clan ties, the rigid political network effectively overlays and overrides the fluid digital network. Now we outline the exact mathematical process an agent undergoes during each step of the simulation to make an adoption decision. This is the interface of the simulation environment, where these rules are parameterized and monitored. In the first evaluation step, an agent calculates the average political trust level of their immediate local neighborhood. The model introduces theta resolution. This acts as the mathematical representation of an agent's stubbornness, or their innate resistance to changing their mind. The agent applies a delta rule. They will only update their internal trust value if their neighborhood's average exceeds their current trust level plus their personal theta resolution. If this updated trust value surpasses their baseline threshold, they adopt the technology. The decision is driven entirely by a localized social cascade. When the model runs, we see a rapid cascade of agents in the network interacting, changing their state, and eventually reaching a frozen equilibrium point. These charts presenting the resulting function of adoption plotted across the multidimensional space generated by the simulation. By looking at the top left chart, we can identify the emergent macro behavior. The system definitively does not yield a smooth Rogers diffusion curve. Total adoption remains near zero until the ratio of politically trustful citizens hits a strict threshold, roughly twice the number of distrustful citizens. Once this specific 2-to-1 threshold is breached, the resistance breaks and a massive social bandwagoning cascade finally occurs. These alternate scatter plots show that increasing the theta resolution to make agents more stubborn slightly smooths out this sudden cliff, but the phase transition remains intact. This proves that mass adoption of civic tech requires a critical mass of political trust to trigger the cascade, overriding all other variables in the system. We can now shift the analytical focus to the x-axis of these scatter plots, which tracks the baseline technological affinity of the population. Across all simulation runs, the adoption curve along this specific axis is incredibly flat and uniform. The implication here is that the baseline enthusiasm for technology in a city barely impacts the final macro adoption state of a smart city project. When privacy is at stake, rigid, clan-based political network dynamics entirely supersede digital tech advocacy. For policymakers deploying privacy-invading civic tech, simple data on tech preferences offers little predictive value. Instead, political trust serves as the non-negotiable barrier that determines whether a project succeeds or fails.